I was trying to get you to visualize and get myself to visualize a ion that was trapped in a quadrupole, which was let's just say it's a device that uses magnetic fields, electrostatic, magnetic, I think it's magnetic fields that hold it in position. When it's held in position, the particle or the ion or the atom acts like it's a mass in a harmonic oscillator and moves back and forth. So this video is going to try to just talk about a oscillator on a spring, and this is to try to prevent the math from making our eyes glaze over. Okay, math time. Let's see if you can make some sense of this. Mass. Spring constant. The larger the spring constant, the stiffer the spring. And remember, we're using a spring now, but later on we're going to forget about the spring, and we're going to forget about a regular mass, but we're going to talk about a ion. So it's going to be really small stuff, and this is going to change a little bit. X as a function of time is the displacement of the equilibrium at time t. You look at the symbols and see if you feel okay with it. Anyway, F equals ma. That is the second law of Newton's second law. This does pretty well explain it. And here's negative kx as a function of time. So that shows that the force is going to be opposite the displacement. You push it to the right, it's going to tend to pull it back to the left. You push it to the left, it's going to tend to push it towards the right. Now here's where it gets really ugly. Second derivative of x with respect to time. How do we get from here to there? Well, this is an expression of acceleration. Acceleration is the rate of change of velocity, increasing velocity or decreasing velocity. Acceleration is zero if the velocity isn't changing, and velocity is the change of distance with respect to time. So it's the change of a change of that, and this thing stays the same. Now, what we did we jump from here to here, and how did all that occur? How did that all occur? Well, if this is negative kx and we divide it by m, then we get negative km down here. So we square whatever this thing is, and we get negative km. So how do we get a negative km out of this thing? Well, if you take the square root and square it, you get k over m. If you take the square root of 1 and square it, you get negative 1. Square root of 1, what's that? That is imaginary. But the definition of the imaginary unit is if you square it, then you get back to negative. So that's what all of this stuff is. Now, I'm going to change this step a little bit and show you my notebook. There's Hooke's law. There's Newton's second law. So this is all the same stuff. This is all the same stuff here. And then this is the same stuff. Now this is something new. The base of the natural logarithm to the x power, if you take the first derivative with respect to x, you just get right back to e of x. If you take the derivative of e, where x is a function of time with respect to time, then you get e to the x of t, but you have to multiply that times the derivative of x with respect to t. Here's e to the I of x equals cosine x plus I sine x. This is just a Euler's identity, which is very important. Also, if we let x equal omega, omega stands for 2 pi times the frequency. So let's see if we can take this information and go back to the other screen. Okay, eventually what we're going to get to is we're going to have an I sine of this function omega t. Amazingly, it did come up with e to the I omega t and e to the negative I omega t. And what's our solution? Single mass on a spring, where omega is square root of k over m, so we can use that to figure out how fast the thing oscillates. And the oscillation rate is what we're really interested in. How do we do on trying to make sense of that? I would say, I thought we did okay with it. So that's a regular spring. And now what we're going to do is apply it to a ion that's springing back and forth in an RF field.